All right, so let's talk about angle measurements and finding the position of radian measurements on a unit circle. So let's start with the unit circle. I'm going to center that a little bit better so it's not so annoying. Again, it's a unit circle, so this would be 1, 0. And this would be -1, 0, and so on. So if we were looking for the angle 11 pi over 4, what we need to do is we need to break down this into pi over 4 sections. And if you don't know what pi over 4 is, pi is 180. Divide that by 4 and you should get 45 degrees. So if you can divide your circle into 45-degree sections, it would kind of look a little bit like this. And again, I'm going to try to center those as best I can. And what we have is we're going to start here at 1, 0, and we're going to rotate in a counterclockwise direction, and we're going to stop every pi over 4. That's what these sections are for, and we're going to do that 11 times, and that's going to be our ending position. So starting at 1, 0, we have 1 pi over 4, 2 pi over 4, 3, 4, 5, 6, 7, 8. Okay, that's an important stopping point, right? So every 8 pi over 4 is 1 full revolution. And then 9, 10, 11. So my stopping point is here. This is the same as 11 pi over 4, that point. It's the same as 3 pi over 4, right? They're the same position. I just have a different magnitude of the rotation for 11 pi over 4. Let's do another one. Let's go -32 pi over 3. Now pi over 3 is equal to 60 degrees. So I know that there are 3 160s in a 180 degrees, so half a circle would be 3 sections. So I'm going to do 6 sections for the full circle. So it's going to look like this. I look at it as like a Trivial Pursuit game piece. Okay, and I need to do -32 pi over 3s. So I could literally just count, again, negative being in the clockwise direction. I can count by 6s, right? So there's 6 to get here. 12, 18, 24, 30, and then 1, 2 would put me here. So that would be my stopping point for -32 pi over 3. -32 pi over 3 is there. It's the same as -2 pi over 3. Same location, different magnitude. And again, the magnitude isn't all that important for us right now. What happens if it's just a ginormous number? Ginormous, not even a real word. 137 pi over 6. So pi over 6, we are actually going to, I'm just going to put the markings here, would be 3 stops per quadrant, or actually two stops in the quadrant, and then you're also stopping at each of the axes. So there's 12 stopping points on the entire circle, okay? And to me, this looks like a clock. So each of those would be the hands of a clock, but we're starting at, again, 1, 0 over here. So you could count 137 rotations, right? So our turns, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I don't have time to do that, and I'm going to have a lot of dots there. So let's not do that. Let's find a better way. I know that 137 is 120 plus 17. So I know 120 would be 10 times around. 10 revolutions is 120 pi over 6. So then I'd be left with doing only 17, which is a much more manageable number. In fact, I could even go 132 is 11 revolutions, right? 132 pi over 6 is 11 revolutions because there's 12 pi over 6 per revolution, which would leave me 5 pi over 6 extra. I think 17 is manageable. This would be a few less, so whichever works for you. So just to kind of write it out in terms, we can actually do it in any combination we want as long as the total equals 137. So I can look at it as 120 pi over 6 plus 17 pi over 6, or slightly quicker would be 132 pi over 6 plus 5 pi over 6. And in either case, those first two have me going around a bunch of times, but stopping here. And then I have to do an additional 1, 2, 3, 4, 5 pi over 6 for the second one. So my stopping point is right there. That's 137 pi over 6. It just happens to be in the right spot. So that's finding the location.